The voltage drop formula is volts equals I times R times D divided by rho times A. In this formula, V represents the voltage drop in volts, I represents the current in amps, R represents the resistance of the conductor in ohms, D represents the distance in feet, rho represents the resistivity of the conductor material in ohm feet, and A represents the cross-sectional area of the conductor in circular mils. To calculate resistance, use the formula R equals rho times L divided by A, where L represents the length of the conductor in feet. The resistivity of copper at 77 degrees Fahrenheit or 25 degrees Celsius is 10.37 ohm feet. Let's apply these formulas to a scenario. Consider a 100 amp load being supplied by a #2 copper conductor over a distance of 160 feet. We will assume the resistivity of copper is 10.37 ohm feet. The formula for voltage drop can be represented as volts equals 100 amps times 160 feet times 10.37 ohm feet divided by 13,608 circular mils, which is the approximate circular mil area of number 2 AWG copper wire. In this case, the calculation yields a voltage drop of approximately 18.9 volts. Let's break that down further. Firstly, it is important to understand the components of the voltage drop formula. The current I represents the electrical load in amps that the circuit is expected to carry. This value is crucial for determining the appropriate wire size and for calculating voltage drop. Secondly, the resistance R is the opposition to the flow of current in the conductor. Resistance depends on the material of the conductor, its length, and its cross-sectional area. Copper and aluminum are commonly used conductors due to their relatively low resistance. Thirdly, the distance D is the one-way length of the conductor from the source to the load. Voltage drop increases with distance, so longer runs require careful consideration. Fourthly, resistivity ρ is an intrinsic property of the conductor material that quantifies how strongly it resists electric current. Copper has a lower resistivity than aluminum, making it a better conductor. The value of 10.37 ohm feet is a standard value for copper at a specific temperature. Fifthly, the cross-sectional area is the area of the conductor perpendicular to the direction of current flow, measured in circular mils. A larger cross-sectional area reduces resistance and voltage drop. Wire gauge sizes are directly related to their cross-sectional areas. The formula for calculating resistance, R equals rho times L divided by A, is derived from Ohm's law and the properties of the conductor. This formula allows to determine the resistance of a conductor based on its material properties, length, and cross-sectional area. Using the example of a 100 amp load, 160 feet distance, and #2 copper wire, the calculation provides an approximate voltage drop of 18.9 volts. This means that the voltage at the load end of the conductor will be 18.9 volts less than the source voltage. For instance, if the source voltage is 120 volts, the voltage at the load will be approximately 101.1 volts. It is crucial to ensure that the voltage drop does not exceed acceptable limits, typically 3% for branch circuits and 5% for feeders, to prevent equipment malfunction or damage. Several factors can influence voltage drop calculations. Temperature affects the resistivity of the conductor material. Higher temperatures increase resistivity, leading to higher voltage drop. The type of insulation used on the conductor can also impact voltage drop, as it affects the operating temperature of the conductor. The presence of harmonics in the electrical system can increase voltage drop due to increased current flow. When performing voltage drop calculations, it is important to use accurate values for all the parameters involved. Using incorrect values can lead to inaccurate results and potentially unsafe wiring practices. Online voltage drop calculators and software tools can assist in performing these calculations. These tools typically require inputting the load current, conductor length, wire size, and conductor material. They automatically calculate the voltage drop and provide a report of the results. The NEC, National Electrical Code, provides guidelines and requirements for voltage drop in electrical systems. It recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Adhering to these recommendations helps ensure proper equipment operation and prevents safety hazards. There are several methods to reduce voltage drop in electrical circuits. One method is to increase the size of the conductor. A larger conductor has a lower resistance, which reduces voltage drop. Another method is to shorten the length of the conductor. Shorter runs result in lower voltage drop. Increasing the supply voltage can also reduce voltage drop, as it reduces the current required to deliver the same amount of power. Using conductors with lower resistivity, such as copper instead of aluminum, can also minimize voltage drop. In addition to voltage drop calculations, it is also important to consider ampacity when sizing conductors. Ampacity is the current carrying capacity of a conductor. The NEC provides ampacity tables that specify the allowable ampacity for different wire sizes and insulation types. The conductor must be sized large enough to carry the load current without exceeding its ampacity rating. Exceeding the ampacity rating can cause the conductor to overheat, potentially leading to insulation damage or fire. When selecting a conductor size, it is crucial to consider both voltage drop and ampacity requirements. The conductor must be large enough to meet both criteria. In some cases, the conductor size required for voltage drop may be larger than the size required for ampacity. In such cases, the larger conductor size must be selected. Proper grounding is also essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and clear the fault. Grounding conductors must be sized according to the NEC requirements. Incorrectly sized grounding conductors can compromise the effectiveness of the grounding system. Regular inspection and maintenance of electrical systems are important for ensuring the continued safety and reliability. Inspection should include checking for loose connections, damaged insulation, and signs of overheating. Maintenance should include tightening connections, replacing damaged components, and cleaning equipment. Proper documentation of electrical systems is also crucial. Documentation should include wiring diagrams, panel schedules, and equipment specifications. This documentation is essential for troubleshooting and maintenance purposes. The voltage drop formula and related concepts are fundamental to electrical engineering and wiring practices. Understanding these concepts is essential for designing and installing safe and efficient electrical systems. By applying the principles discussed here, it is possible to minimize voltage drop, ensure proper equipment operation, and prevent electrical hazards. Electrical work should always be performed by qualified and licensed electricians. Working with electricity can be dangerous, and it is important to take all necessary safety precautions. Always de-energize circuits before working on them and use appropriate personal protective equipment such as gloves and eye protection. In summary, calculating voltage drop is a critical aspect of electrical design and installation. Using the voltage drop formula, understanding the factors that influence voltage drop, and applying appropriate mitigation techniques can help ensure safe and efficient electrical systems. Remember to always consult the NEC and follow local electrical codes when performing electrical work. Consider the specific application and load requirements when selecting conductor sizes and materials. Regular inspection and maintenance are essential for maintaining the safety and reliability of electrical systems. Understanding and applying these principles will contribute to the safer and effective use of electricity. Using the earlier example, the voltage drop of 18.9 volts should be taken into consideration in the overall design. A voltage drop of 18.9 volts on a 120 volt circuit results in about a 15.75% drop. This is far above the recommended limits as discussed earlier in this discussion. This illustrates the need to increase the wire size to reduce the voltage drop in this example. For example, the circular mill area of a number 1 AWG copper wire is 20,820 circular mils. Using the voltage drop formula with this new value, volts equals 100 amps times 160 feet times 10.37 ohm feet, divided by 20,820 circular mils, the voltage drop would be equal to 7.97 volts. This results in a voltage drop of about 6.64%. This is still slightly above the recommendation of 5% for feeders, as discussed earlier. It should be noted that the 5% recommendation is for the total voltage drop, considering the source to the panel as well. As a result, using a number 1 AWG copper conductor could be acceptable in this case. The circular mill area of a number 1/0 AWG copper wire is 26,240 circular mils. Using the voltage drop formula again with this new value, volts equals 100 amps times 160 feet times 10.37 ohm feet divided by 26,240 circular mils, the voltage drop would be equal to 6.32 volts. This results in a voltage drop of about 5.27%. This is much closer to being within the recommendations. This further illustrates the need to consider wire size when deciding what conductor to use. The actual voltage drop observed may vary due to a number of factors. Firstly, the actual load current may differ from the calculated value. Secondly, variations in conductor temperature can affect resistance. Thirdly, the presence of harmonics can increase voltage drop. It is always recommended to err on the side of caution and use a larger conductor size if there is any uncertainty. The voltage drop formula provides a valuable tool for electrical design and analysis. By understanding the principles behind the formula and applying it correctly, electrical professionals can ensure the safe and efficient operation of electrical systems. Remember to always prioritize safety and consult with qualified professionals when working with electricity. The resistivity of copper is affected by temperature, which influences voltage drop. At higher temperatures, the resistivity of copper increases, resulting in a greater voltage drop for the same current and conductor size. Conversely, at lower temperatures, the resistivity decreases, leading to a smaller voltage drop. Therefore, it's important to consider the operating temperature of the conductor when performing voltage drop calculations, especially in environments with extreme temperatures. The type of load connected to the circuit can also affect voltage drop. Linear loads, such as resistive heating elements and incandescent lights, draw current in a sinusoidal waveform, making voltage drop calculations straightforward. Nonlinear loads, such as electronic devices with switching power supplies, draw current in a non-sinusoidal waveform, which can introduce harmonics into the circuit. Harmonics increase the RMS current and can lead to higher voltage drop than predicted by the standard voltage drop formula. When dealing with nonlinear loads, it may be necessary to use more sophisticated methods for calculating voltage drop, such as harmonic analysis software. Conduit fill refers to the percentage of space inside an electrical conduit that is occupied by conductors. The NEC specifies maximum conduit fill percentages to ensure adequate heat dissipation and prevent damage to conductors. Higher conduit fill can lead to increased conductor temperature, which affects resistivity and voltage drop. Therefore, it's important to consider conduit fill when selecting conductor sizes and performing voltage drop calculations. Voltage drop can also be affected by the presence of multiple conductors in a single conduit or cable. When multiple conductors are carrying current, their magnetic fields can interact, leading to increased impedance and voltage drop. This effect is more pronounced when the conductors are closely spaced or when they carry high currents. The NEC provides adjustment factors for ampacity based on the number of conductors in a conduit or cable. These adjustment factors should be applied when calculating voltage drop to account for the increased impedance. Voltage drop is not only a concern for power circuits but also for control circuits and signal circuits. In control circuits, excessive voltage drop can cause relays and contactors to malfunction, leading to equipment failure. In signal circuits, voltage drop can degrade the signal quality, resulting in inaccurate readings or unreliable communication. Therefore, it's important to consider voltage drop in all types of electrical circuits, not just power circuits. The voltage drop formula assumes a purely resistive load. In reality, most electrical loads have both resistive and reactive components. Reactive loads, such as motors and transformers, draw current that is out of phase with the voltage, leading to a more complex voltage drop calculation. To accurately calculate voltage drop in circuits with reactive loads, it's necessary to use vector analysis or impedance calculations. Software tools are available to simplify these calculations. The concept of voltage drop is closely related to the concept of power loss. When voltage drop occurs in a conductor, electrical energy is dissipated as heat due to the resistance of the conductor. This power loss is proportional to the square of the current and the resistance of the conductor. Minimizing voltage drop helps to reduce power loss and improve the efficiency of the electrical system. The cost of energy losses due to voltage drop can be significant over the lifetime of an electrical system. Therefore, it's important to consider the economic implications of voltage drop when designing and installing electrical systems. Investing in larger conductor sizes or shorter runs can reduce voltage drop and save energy costs in the long run. Voltage drop calculations are an essential part of electrical design and should be performed for all circuits to ensure safe and efficient operation. By understanding the factors that affect voltage drop and applying appropriate mitigation techniques, electrical professionals can minimize voltage drop, reduce power losses, and improve the reliability of electrical systems. Remember to always consult the NEC and follow local electrical codes when performing electrical work. The NEC guidelines for voltage drop are recommendations, not mandatory requirements. However, it's generally good practice to adhere to these recommendations to ensure proper equipment operation and prevent safety hazards. Some jurisdictions may have stricter voltage drop requirements than the NEC, so it's important to check local codes and regulations. In addition to the voltage drop formula, there are other methods for calculating voltage drop, such as using voltage drop tables or software tools. Voltage drop tables provide pre-calculated voltage drop values for various conductor sizes, lengths, and current levels. Software tools can perform more complex voltage drop calculations, taking into account factors such as temperature, conduit fill, and harmonics. These alternative methods can be useful for simplifying voltage drop calculations, especially in complex electrical systems. Voltage drop is not a static value but can vary depending on the load current. As the load current increases, the voltage drop also increases. Therefore, it's important to consider the expected range of load current when performing voltage drop calculations. The maximum voltage drop should be calculated based on the maximum expected load current. The voltage drop formula is based on the assumption of a constant current flow. In reality, the current flow in electrical circuits can fluctuate due to changes in the load. These fluctuations can affect the voltage drop and may need to be considered in critical applications. Specialized equipment, such as voltage regulators, can be used to compensate for voltage drop and maintain a stable voltage at the load. Voltage regulators are commonly used in applications where voltage fluctuations can have a significant impact on equipment performance, such as in sensitive electronic equipment or medical devices. The NEC provides guidelines for the installation of voltage regulators, including requirements for overcurrent protection and grounding. The effects of voltage drop can be particularly problematic in long branch circuits. In long branch circuits, the voltage drop can be significant, leading to reduced equipment performance and potential safety hazards. To mitigate the effects of voltage drop in long branch circuits, it's often necessary to use larger conductor sizes or install additional branch circuits. The NEC provides specific requirements for long branch circuits, including limitations on the length of the circuit and the number of outlets allowed. The voltage drop formula can be used to calculate the voltage drop in three-phase circuits, but the calculations are slightly more complex than for single-phase circuits. In three-phase circuits, the voltage drop depends on the type of load connection Y or delta and the phase angle between the voltage and current. Specialized software tools are available to simplify voltage drop calculations in three-phase circuits. The voltage drop formula assumes that the conductor is made of a homogeneous material with a uniform cross-sectional area. In reality, conductors may have imperfections or variations in their composition or geometry. These imperfections can affect the resistance of the conductor and may need to be considered in critical applications. The NEC provides tolerances for conductor resistance, which should be taken into account when performing voltage drop calculations. In some cases, it may be necessary to perform field measurements of voltage drop to verify the accuracy of the calculations. Field measurements can be used to identify unexpected sources of voltage drop or to validate the performance of voltage regulators. Specialized equipment, such as voltage recorders, can be used to monitor voltage drop over time. The voltage drop formula is a simplified model of a complex phenomenon. While it provides a useful tool for estimating voltage drop, it's important to understand its limitations and to consider other factors that may affect voltage drop in real-world applications. By combining the voltage drop formula with sound engineering judgment and practical experience, electrical professionals can ensure the safe and efficient operation of electrical systems. It is important to ensure that all electrical connections are tight and properly made. Loose connections can increase resistance and contribute to voltage drop. Regular inspections and maintenance of electrical connections can help to prevent voltage drop problems. The use of high-quality connectors and proper installation techniques can also minimize voltage drop. The voltage drop formula can be used to optimize the design of electrical systems for energy efficiency. By minimizing voltage drop, it's possible to reduce power losses and improve the overall efficiency of the system. This can lead to significant cost savings over the lifetime of the system. The increasing use of renewable energy sources, such as solar and wind power, is creating new challenges for voltage drop management. Renewable energy sources can introduce voltage fluctuations into the electrical grid, which can affect the performance of sensitive equipment. Advanced control systems and voltage regulators are being developed to address these challenges. The NEC provides specific requirements for the interconnection of renewable energy sources to the electrical grid, including requirements for voltage regulation and overcurrent protection. The voltage drop formula is a valuable tool for understanding and managing voltage drop in electrical systems. By applying the principles discussed here, electrical professionals can ensure the safe, efficient, and reliable operation of electrical systems in a wide range of applications.